Procedural generation is a method of creating content for video games and other digital media using formulas and algorithms, rather than creating these features by hand. This can be applied to many different types of content creation, from terrain to level design and even trees. This video will primarily focus on terrain generation. Well, how is this done? There are many different ways of doing this, but a common way of creating terrain is through heightmap displacement of a flat 2D mesh. Height maps are a way of encoding the height of some point on a 2D surface into an image. These height maps are applied to a mesh as shown in the image on screen, whereby white pixels are made to be higher and black pixels are made to be lower. This method of creating terrain is also extremely lightweight. So then everything is perfect, right? Not quite. This form of terrain generation does have some of its own issues. These can be boiled down into two major categories: distortion and impossible geometries. Distortion comes as a result of the nature of the generation method. As the squares are of a fixed width, the only way for them to be able to reach higher areas is to elongate and stretch, which can lead to ugly looking meshes and a loss of resolution. The pictures shown on the left demonstrate this, with the far left image showing a piece of mesh that is at 70 degrees, and it is 3.7 times longer than it should be ideally. The other problem is geometry that is physically impossible to create, for instance caves, cliff faces, sea arches, and so on. Vertical faces and overhangs cannot be achieved using this method, limiting designers in what they can do. So, how could we fix this? By utilizing the third dimension and using voxels. Volumetric pixels, or voxels, are the three-dimensional equivalent of pixels, where at regularly spaced points in R3 space there is a scalar value. These values can be treated like densities, as could be seen in the right picture, with darker dots representing higher values. However, a computer cannot render densities into an image directly. This needs to be converted into a bunch of triangles first. A common way of achieving this is through the marching cubes algorithm, first published by Lorentzen and Klein in 1987. This method involves trying to create a three-dimensional surface that separates all the points in the data field that are above a threshold from those that are below. This is tackled by looking at one cube of the data field at a time. The image shows all the possible configurations of corners that are above or below the threshold. This is repeated until all the cubes have been accounted for, resulting in a complete mesh. But how do GANs relate? Generative adversarial networks, or GANs, operate by having two opposing networks, one that will attempt to create forgeries of the training data, while the other will be attempting to learn which examples are real or fake. This leads to a network that can create examples of the input data with astonishing accuracy. GANs have been shown to learn terrain height map images and be able to replicate them with stunning results as shown in the images, with the training image being on the left with the various generated examples shown to the right of it. This was done by Ryan Spick, Peter Cowling, and James Walker back in 2019. However, their method was still only using 2D height maps and not true 3D data. This is where my research comes in, finding if it is viable to use voxels for the creation of terrain using GANs. To begin this process, I needed data, and lots of it, specifically 27 million square kilometers of it. The area chosen is shown in pink on the screen. It covered most of Africa, as I wanted to keep topological features consistent. The data used for this was required from the NASA Shuttle radar topology mission that took place in 2000. This dataset contains high-resolution height maps of the Earth's surface, down to an accuracy of 30 meters. These images were then cut up, contrast shifted, and converted into both a 2D height map and a voxel dataspace. An example of this data shown above. The pictured renders are from a river valley in the DRC. All in all, this resulted in 96,562 individual examples of training data. Using these two datasets, two distinct networks were tested, one that would attempt to learn the 2D height maps, and the other would attempt to learn the voxel data fields. The architectures were kept as similar as possible to help facilitate comparisons between the two. The network pictured is the larger 3D voxel network, but both consisted of 5 layers of either increasing or decreasing depth. The two models were trained on their respective datasets, and some examples of their output are shown. The 2D network seemed to latch onto features like rivers and valleys, while the 3D network preferred islands and peninsulas. This trend seemed to follow even after doing multiple different runs. Even though this method is promising in this visual regard, noise is a problem. In the 2D case, noise is easy to deal with, as it will blend into the rest of the environment, while in the 3D case, noise will appear as floating, disconnected blobs. However, this could be mitigated by culling objects smaller than some specific threshold. To see which network had a smaller amount of distortion, the lengths of the various edges of the mesh were measured and averaged. Smaller values meant less vertices that were being stretched more than necessary. For example, the image shown on the leftmost square would have a score of 1.138, while the other having a score of 2.863. This analysis method was then applied to a spread of 64 different examples from both networks. This resulted in the table shown, and as can be seen, the 3D case would have on average a smaller amount of distortion when compared to the 2D method, although the variance did seem to be higher with the 3D case. To take this further, one could definitely use a larger network to try and learn larger data fields, as this setup was limited by the amount of VRAM available. Another potential avenue would be to explore having hybrid generators that would use a more complex form of number generation in the process of creating its latent vectors, rather than just pure random numbers. The main takeaway is that the usage of voxels in terrain generation is promising, and shows that the usage of truly 3D terrain generation is viable if just resource intensive. Overall, for faster training and faster rasterization, 2D heightmap generation works the best. Otherwise, the use of 3D generation would work.